In May 2013, NASA's Kepler Space Telescope lost the second of the 4 reaction wheels that held its gaze steady. The spacecraft was still communicating, its camera still worked, and sunlight still powered it. Yet the original planet hunt depended on measuring tiny dips in starlight while Kepler stared continuously at one patch of sky. With only 2 healthy wheels, the telescope could no longer resist a push from the Sun in all 3 axes. A mission designed to find other worlds had become a working observatory that could not hold still. Engineers eventually recovered it by treating the force that disturbed Kepler as part of the control system. Kepler launched in March 2009 with a 0.95-meter telescope and a field of view covering roughly 100 square degrees. Its method was simple to describe and hard to execute. It watched the brightness of more than 100,000 stars, looking for the slight, repeated dimming produced when a planet crossed a star's face. A transit might reduce the measured light by only a small fraction of 1%. To compare one observation with the next, the same stellar images had to remain on nearly the same detector pixels for months and years. Pointing was therefore not merely about keeping the target somewhere in the camera. It was part of the measurement itself. Kepler used 4 reaction wheels arranged with 1 spare. By accelerating or slowing a spinning wheel, the spacecraft could rotate in the opposite direction without expelling propellant. 3 working wheels were needed for precise control around 3 axes. The 4th provided redundancy, but not immunity from 2 failures. Reaction wheel number 2 failed in July 2012. Kepler could continue because the remaining 3 wheels still supplied the minimum set for full 3-axis control. NASA extended the mission in November after the observatory completed its planned prime mission. The extension mattered scientifically. Longer observation increased the chance of seeing planets with wider, more Earth-like orbits make enough transits to be confirmed. It also meant the spacecraft was operating with no remaining wheel redundancy. Engineers monitored the wheels, adjusted operating procedures, and knew that another loss would end the original observing method. In early 2013, wheel number 4 showed elevated friction. Controllers tried techniques intended to redistribute lubricant and reduce resistance, but on May 11 the spacecraft entered safe mode. When contact was restored, wheel 4 would not spin. NASA later ended attempts to recover either failed wheel. The observatory had completed 4 years of continuous monitoring, but it could no longer maintain the precision required in its fixed Cygnus field. A reaction wheel controls rotation around an axis. 2 wheels could govern 2 components of Kepler's attitude, but the remaining roll direction was exposed. Thrusters could correct the roll, yet firing them continuously would consume the limited hydrazine supply and disturb the delicate photometry. The persistent external force was sunlight. Photons carry momentum, so radiation pressure produces a small push on every illuminated surface. Kepler's broad solar array made that push significant enough to twist the spacecraft. In the original mission, 3 wheels absorbed the resulting torque and were periodically unloaded with thrusters. With 2 wheels, the torque around the uncontrolled axis made stars drift across detector pixels. The vehicle was not tumbling uncontrollably, it was failing a much stricter requirement. Even small drift changes how light falls across pixels with slightly different responses. A telescope can remain pointed toward the correct constellation and still be too unstable to make its intended measurement. The recovery idea began by changing the geometry rather than replacing hardware that could never be reached. Kepler was approximately symmetric about the ridge of its solar panels. If controllers pointed the telescope near the plane of its orbit around the Sun, the ecliptic sunlight would strike the 2 sides in a more balanced way. Radiation pressure would still exist, but the torques around the uncontrolled roll axis could nearly cancel. The 2 surviving reaction wheels would control the other axes. Small residual roll drift could be corrected with brief thruster firings instead of continuous propulsion. In effect, the Sun could provide a stabilizing reference where it had previously been a disturbance. NASA described the concept as using solar pressure like a virtual third wheel. That phrase is useful but not literal. Sunlight did not actively turn the spacecraft on command. Engineers oriented the vehicle so its shape passively reduced the torque, then used wheels and periodic thruster corrections to manage what remained. The idea had to survive tests on the actual spacecraft. Engineers measured how stable Kepler could remain with two wheels, selected attitudes that balanced illumination, and evaluated whether the resulting motion could be corrected in data processing. The telescope could not return to its original northern field indefinitely because the safe balanced direction changed as Kepler orbited the Sun. Instead, it would observe a succession of fields along the ecliptic. Each campaign could last about 80 days before the spacecraft rotated to maintain safe Sun angles and point at a new field. NASA invited the scientific community to propose uses for this altered observatory. The design traded one continuous field for many shorter campaigns. That reduced sensitivity to exact Earth analogs on year-long orbits, but opened bright nearby stars, clusters, supernovae, galaxies, and objects within the solar system to observation. Recovery required redefining success around the control authority the spacecraft still possessed. NASA approved the K2 mission in 2014. During a campaign, controllers placed the telescope with its bore sight close to the ecliptic plane and chose a roll angle that minimized solar torque. The two reaction wheels maintained pitch and yaw. Residual roll motion slowly shifted star images, and thrusters corrected that drift at regular intervals. The resulting pointing was less stable than Kepler's original performance, so scientists developed calibration methods that related brightness changes to measured image position. A repeated instrumental signature could then be separated from an astrophysical signal. This was not a restoration of the old observatory. It was a new operating mode combining passive balance, sparse propulsion, and revised analysis. The fix worked because each layer addressed a different part of the problem. Spacecraft orientation reduced the disturbance, the remaining wheels controlled two axes, thrusters bounded the third, and software corrected systematic effects left in the measurements. The ecliptic was initially a pointing constraint, but it became the map for a new survey. K2 moved from field to field in campaigns, allowing different research teams to nominate targets. Nearby red dwarfs, young star clusters, exploding stars, active galaxies, asteroids, and comets entered the program. The mission found planets around bright stars that were attractive for follow-up observations. In December 2014, NASA announced K2's first confirmed exoplanet, HIP 116454b. The spacecraft ultimately completed 19 campaigns, far more than the 10 initially estimated on its remaining fuel. Across Kepler and K2, the observatory surveyed more than 500,000 stars. The change in mission design did not erase the loss. K2's shorter campaigns and different precision created real limits. But the wider sky coverage and community-led target selection produced science the original fixed-field survey was never designed to collect. It is tempting to describe the recovery as one clever insight: let sunlight become the third wheel. The operational achievement was broader. The spacecraft had safe modes that preserved it after the wheel failure. It retained commandable thrusters, healthy power, communications, and a functioning photometer. Engineers could characterize its new dynamics in flight. Scientists were willing to redesign observing programs and data pipelines around a different noise environment. Mission management accepted a proposal whose measurements and targets would differ from the original promise. Each of these was a form of recoverability. Hardware redundancy bought time after the first failure, but adaptability after the second failure came from understanding which requirements were fundamental and which could change. Kepler could no longer stare at one field with its former stability. It could still measure repeated changes in light if the pointing disturbance became predictable enough to model. Kepler exhausted its usable fuel in 2018 and NASA retired it in a safe orbit after more than 9 years of operation. The mission left more than 2,600 confirmed planet discoveries, with K2 also contributing planets and a much broader range of time domain observations. Its recovery offers a precise engineering lesson. A failed component does not define the only possible function of a system. Engineers first separated the lost capability, continuous ultrastable 3-axis pointing, from the assets that remained. They then shaped the environment, the operations, and the data analysis to close that gap together. The most elegant part was not overpowering solar radiation pressure. It was arranging the spacecraft so that the force almost balanced itself. Kepler's second mission came from accepting that the observatory would move, deciding where that motion could be smallest, and teaching the science pipeline to understand what motion remained.